Hi all, welcome to the world's best NLP presentation, a presentation on the Spacey package for Python. Spacey provides out-of-the-box advanced NLP functionality. It's an industrial-grade, efficient NLP Python library, including various pre-trained models and ready-to-use features. As a general overview, Spacey was developed in 2015 by Explosion AI, who also create other tools that interact with Spacey. It's published under the MIT license, which allows for commercial use. The last stable version is version 3, which was released on February 2021. This update included compatibility with Hugging Face. It has huge online support. For example, it has more than 23 million downloads and approximately 22,000 stars on GitHub. Lastly, and best of all, it's Berlin-based. For a brief agenda of this presentation, we will cover some background and history to the package, an explanation of Spacey's pre-processing pipeline and basic components, and then we'll go through some of Spacey's extra functionality. However, before we continue with the presentation, it might be worth understanding what NLP actually is. NLP, also known as natural language processing, is a subfield of artificial intelligence that analyzes text, speech, and other forms of human-generated data. For example, you can see in this diagram provided in Spacey's textbook, shows how a very simple sentence can be broken down into several components, which could all have their subjective meaning. NLP helps us better understand these sentences. Now, it might be worth understanding when we should use Spacey. Spacey shows its clear advantage when working with large amounts of unstructured data and when you want to quickly know more about this text. The slide provides a few examples of what we might want to know about, including sentiment analysis and similarity. Spacey can also be used to build information extraction systems, natural language understanding systems, or to pre-process text for deep learning. Believe it or not, Spacey might have some competition who are listed in this slide and include popular NLTK, an NLP package with an academic focus. But of course, Spacey beats out these competitors in terms of speed and out-of-the-box features. However, debate exists as to which tool is the most customizable or accurate. To demonstrate Spacey's edge, we can see that it is the fastest package to tokenize, tag, and parse text when compared to core NLP, ZPAR, and NLTK. Further, Spacey comes with more out-of-the-box functionality when compared to NLTK or core NLP, such as integrated word vectors and entity linking. Some of Spacey's features which makes NLP easy is the inclusion of processing pipelines for over 60 languages, the ability to choose multiple models for each language, the provision of end-to-end workflows in the form of project templates, and compatibility with adjacent NLP tools such as Prodigy and Hugging Face Hub. Now Kabir will go through the installation and initial use of Spacey.
All right, thank you for that, Viraj. I'm sure everybody can't wait for the next part of this. So we'll move on to the pre-processing pipeline and basic components of Spacey. All right, here we are. So here is the basic code to install Spacey. I'm sure these commands will look familiar. And then it's important to know that there are many different language models to work with. We're going to be focusing on the default English model seen here, but we include a hyperlink to other language models. So this is the code to import Spacey, of course. And we're going to save the default English model under the variable name Nlp English, and then we'll see what it's capable of doing. So it has the following abilities, and we'll get into more of what those mean in a second. To start, we came up with a sentence that demonstrates the ability to tokenize. So we run through the sentence and we print each token, the text contained in the token. And we can see that the sentence is separated into its parts, its words, and its punctuation. And then we can go beyond that and extract a lot of important linguistic information. So here we have run it on the same sentence, but we're extracting the index start position of each word. So the first word starts at position 0, for example. Then we get the word itself, and then we get the lemma, which is the linguistic root of a word. So is corresponds to be. The shape of the word is the length plus any capital letters. So we can see that Spacey is 5 letters long with a capital letter, capital C. And then we do a Boolean check of whether it's a stop word, false for Spacey, but true for is. Dependency, we'll talk more about that later, but it relates to grammatic and linguistic dependencies in the sentence. And then finally, there's a Boolean check for whether the token is alphabetical, or in the case of the hashtag, it's clearly not. So these are all useful features to analyze text, and we can delve a little bit more into what they all mean. So to go over again, lemmatization refers to the process of extracting a lemma from inflected variations of a word. And Spacey, interestingly, is also capable of recognizing proper nouns. And in the previous example, we had Spacey and the class DS and A, data structures and algorithms. So if you're wondering what these all mean and you're a bit confused, Spacey includes an explain feature. So you can pass through something into Spacey explain and it'll spell out for you what it means. And here is that exact function. So if you were to pass in DET to Spacey explain, it would tell you that it was a determiner, and ADP is short for add position. So running this back on our sample sentence, we can see that Spacey is a pronoun, is an auxiliary verb, our is also a pronoun, one is a numeral, etc., so on and so forth. So obviously this gets more interesting the longer and more dynamic the text. So we adapted some from the Herdy website on its student body. And passing that text into Spacey, we can separate into a list of sentences. And then with that list, we can perform some interesting analysis. So we can check for stop words and collect them. So first we import the stop words module. And here is an example of the first 15 words in that. So these will look familiar because we've talked about this a bit in our IDS class. And then we can check what stop words are in our text and separate them from the rest of the text. So in this bit, we clean the text for stop words and punctuation and new line characters. And then we can do a frequency analysis of what words show up the most. And we see, of course, that students, public, and school are up there, along with something else, some other terms that might not surprise anyone. And then we can check how many distinct words are there. So we extract the lemmas, and if we check that they're not punctuation and new line characters, and we can see that there's a total of 129 words in the text, but only 78 unique lemmas. Now moving on to some more sophisticated features.
Okay, so now we're going to take a look at part of speech tagging and specifically assigning word types to tokens. As we've seen already, Spacey can parse and tag any given sentence, and in the part of speech component, every word is assigned to a syntactic category according to the function it has within the sentence. So think of nouns, verbs, adjectives, pronouns, etc. And these sort of categories are called universal tags because they have no language-specific morphological or syntactic features. Like I said, this is sort of where the trained pipeline and the statistical models come in, as they enable Spacey to make predictions as to which tag or label is most likely to apply. POS taggers are sequential statistical models, and this means that the tag of a word depends on the word neighbor's token, their tags, and then the actual word itself. A quick little example to look at. here, if we run this code, we see that the sentence "Apple is looking at buying UK startup for 1 billion" is broken down into text, lemma, POS tags, etc. But we're most interested in the part of speech tag, so that would be the third column, and we can see that Apple is a proper noun, is an auxiliary verb. All this type of information can be accessed like this. This brings us to the next point, which would be dependencies. So purely the POS tags don't provide any information about any words that are not direct neighbors of the tag. And so to highlight sort of the importance of why we should know this is if you had the sentences "I forwarded you an email" and "you forwarded me an email." If you removed any stop words, only forwarded email would be left. However, originally we know that these two sentences had very different meanings and also require very different responses. This is where the dependency parser comes in and helps us delve deeper into the syntax and semantics of a given sentence. What exactly is dependency parsing? Well, it's exactly as the name suggests. It's related to analyzing sentence structures via the dependency between tokens. And a dependency or dependency relation is a direct link between the two tokens. A result of parsing dependencies is always a tree, and it can be visualized using Spacey's built-in Spacey visualizer. So let's take a look of such an example. Here we have, again, our favorite sentence ever. Apple is looking at buying a startup, a UK startup for 1 billion. And you can see that, so for example, Apple and looking are connected by such a dependency arc. And that's because Apple is the noun and looking is the verb that's related specifically to this noun. You can also use this Spacey to visualize long texts. However, then it is advisable to first parse it into a list of sentences, as this will create individual visualizations rather than one long one for the entire text. So yeah, that's useful for longer texts. Now we can move on to named entity recognition, and a named entity is a real-world object that's assigned a name. So it could be a person, a country, a product, or a book, title, anything. And Spacey recognizes various types of named entities in a document by asking the model for prediction. And so this part of the statistic pipeline is called the entity recognizer. And obviously, you should always keep in mind that because these models are statistical, they strongly depend on the type of examples that they were trained on. Therefore, it does not always work perfectly. Just keep this in mind. You might require some tuning later on. Let's have a look at an example. If we run this code, first I've told Spacey to just list all the entities it identifies, and it has done this correctly. So Apple, UK, and $1 billion have been identified. And here it lists them once again, saying the type of entity, in case it is one, and an explanation. So Apple is an organization, the UK is a country, that kind of thing. For a more personal example, I have the following sentence: the Hertie School is located in Berlin, and Hannah Bashara runs the Data Structures and Algorithms class. If we run this, we see Hertie School, Berlin, Hannah Bashara, and Data Structures and Algorithms have all been identified as entities. And if we ask specifically for the 9th entry, we see that Hannah Bashara is in fact a person and not a wizard, although including fictional, so you never know. Yeah, and then as a final step, once again, you can use Spacey to visualize this sort of tagging component. And let me show you quickly how it's done. We use here a Spacey render style entity. Previously, it was dependency, if you remember. And if we run this code, we see that Spacey just highlights according to whichever category the entity is recognized as and visualizes it quite nicely. So that's all on part of speech tagging and named entity recognition. And now we're going to move on again.
All right, let's have a look at the more advanced features of Spacey. First up, rule-based matching. Rule-based matching is basically about finding and extracting patterns from your text. We know a tool for that, regular expressions, sometimes called regex. That is very frustrating and difficult to use. Spacey's rule-based matching engine is way user-friendlier and way easier to use. Comes with a lot more functionality, more powerful because it leverages all the power of Spacey's language models, and comes with linguistic features as well. There is an online demo that we encourage to check out, but let's have a look at some examples ourselves. So basically, this part should look familiar to you. The important line of code is really this one, where we're defining the pattern that we're looking for. This is a nested list with dictionaries in it for each token that we're trying to match here. We're trying to look through this course description of the MDS for the word or for the match data science. Here we're matching the lower attribute of the token. So that first token should be data, small, lowercase, and science, lowercase, in the second token. We're naming that token data science, adding it to the matcher, and let's see what that yields. And it should be successfully identifying data science. Yes, it did. So let's have a look at some more features of the matching engine of Spacey. So it matches all sorts of attributes of the tokens, whether it's an alphanumerical, whether it's a digit, whether that's the start or the end of the sentence, whether it's like a number, like a URL, or like an email. And of course, also can match certain part of speech tags, dependencies, lemmas, and entity types. It supports also some syntax, so whether it is in a vector of strings or not in that vector, whether it's equal to a certain integer or float. So when it comes, for instance, length attribute of a token, that can be useful. It also supports regex-like operators for combining patterns, so matching a pattern once or twice or multiple times, negating a pattern, and of course, you can also use regex as a pattern. How would that look in a more elaborate pattern? Here we're matching first an element of that list. So these are different titles. Then we're matching the entity type person multiple times, operator plus, right, regex operator. And then in the third token, we're matching the part of speech tag verb. And that yields us President Mark Hallerberg wrote. Next up, word vectors. So what is a word vector? It's a very advanced concept of natural language processing. Basically, we're talking here about a representation of a word as a vector of numbers that is computed as the probability of a word occurring based on the words in its context. And basically, it's a long vector of numbers where each number represents a dimension of that word's meaning. Similar words have a very similar vector that can be useful in operations. The standard example here is that the word vector of king minus the word vector of man plus the word vector of woman equals to the word vector of queen, and is very similar to it. And there are different implementations of word vectors. The most famous one is word2vec. Glove is also pretty popular, and Facebook developed one that is called fasttext. These use different algorithms, are technically a little bit different. And well, word vectors can be very difficult to conceptualize and understand because it's very difficult to visualize them since they're high dimensional. There is an implementation of word vector visualizer based on TensorFlow that you can check out. We will do something similar now with a much smaller corpus using the fasttext vectors. Here, first, let's load the module and the language model and parse some string. This is basically just some data words and some policy words concatenated. Let's have a look how a word vector looks like in Spacey. This can be accessed by the vector attribute, and these are based on the language model that we're looking for. So you can see this is just an array of numbers. Not very useful by and of itself, but let's try to visualize these. Here we're just stacking them and doing a principal component analysis to get 3 dimensions that we can visualize. Using Plotly here to plot, we get this graph where each point is a token, and we can kind of see that there is some clusters: government, administration, institution, politics, society are very close to each other. Then there is some coding, programming, informatics. These are also very similar to each other. Data is way out there, policy as well. So that is word vectors. There are a lot of other features and functionalities that Spacey offers. We can't cover them all in our presentation, but we encourage you to check out some of these resources that we use to prepare our presentation that can lead you further. Thank you for your attention, and have fun using Spacey for NLP.